somebody says, "Oh my gosh, human interaction."
Well, as close as we get to it these days. Yes, approximation.
Welcome, everyone. You get to see faces. All right, John, I think you can start at any time now.
All right, fantastic. Well, welcome everyone to LambdaConf 2020 Global Edition. And this week it is my pleasure to introduce to you Dejan, Mijic, who will be discussing declarative concurrency with ZIO STM. So Dejan entered my life about 2 years ago. I don't think we quite determined exactly when, but his first contribution to ZIO was actually a bit of code that involved taking an effect and making sure that it runs where it's supposed to. So for example, if you have an effect that is interacting with a particular database client library and you want to ensure it runs on a database thread pool, then Dejan wrote the first version of the combinator that can do that in ZIO. And then eventually his interest in concurrent programming and distributed programming led him to ZIO STM, where he's been responsible for helping me make a ton of improvements. Like Dejan actually made ZIO STM stack safe for transactions of arbitrary size. He did a lot of work, performance optimization. Actually, I think we increased by like 10 to 100 times performance of certain use cases. And then he also added some really heavy duty, very powerful data structures to ZIO STM. So he's done a lot of stuff, and he definitely knows his stuff. He's very passionate about concurrency, and he's now even gone beyond concurrency, and in his spare time works on ZIO Keeper, among many other projects, helping us build a version of, hopefully, a version of some software that can help us do distributed computations in the ZIO ecosystem at some point in the future. So please help me welcome Dejan.
Thank you, John Courtney, for having me speak at LambdaConf, and thank you for keeping up and organizing the conference during these difficult days for all of us. And of course, thanks to all the attendees. So as John mentioned, tonight I will be speaking about ZIO STM, which is a software transactional memory implementation for our library called ZIO. So, brief introduction about me. I'm a software engineer at LiveIntent, ZIO contributor and trivia collector in the spare time. So if you are keen to discuss software concurrency or some random trivia, feel free to reach out to me. I would like to start the talk with a somewhat mandatory claim that concurrency is terrible, while being more or less mandatory nowadays, because all of us want to make our software scale, to make it more performant, to utilize our resources that we have at our disposal. The claim that concurrency is terrible still somewhat holds. Why is it the fact? Well, first of all, in order to become somewhat of a concurrency expert, you need to pass through a very, very steep learning curve. Also, the software you write usually tends to be error prone, and you end up through many iterations in making the concurrent parts of it correct. And once you made your stable version of your software, you end up with the difficulties to compose the functions you built with the remaining of your services, and then of course, you ended up with the all-long problem of testability, where you end up fixing flaky tests and digging through various thread dumps and trying to make everything happen while your managers are right behind your desk. When we speak about errors that you are encountering while trying to make your software concurrent, there are few, I would say, typical examples. The most important or the most frequent school example are race conditions. Imagine a situation where you are a junior developer and you've been put up with an assignment to make a thread-safe counter. Most likely, for anyone without experience, the first try would look something like this. You would end up with a var, it will be incremented, and it would pass probably your unit tests. But what happens when we put this code snippet in a cross-thread or cross-fiber environment? It's a whole lot of various and unpredictable outcomes. From the first glimpse of from the first short look at this, you would see at least 3 problems. First, you are maintaining a mutable state of a discount variable. Second, you are using non-atomic operations to update it. Third, you will probably end up having some sort of visibility issues when the value is going to be cached in your processor caches instead of being cross-thread visible. Of course, you gain experience and you realize that you can fix this by applying some synchronized blocks and by applying volatiles and by hopefully using immutable states. But then you mature and you end up with different problems. Imagine now a situation where you have to implement a routine for transferring some funds from account A to account B. Imagine also that you use the knowledge that you gained from the previous example and now you know about atomic operations, you are well aware about cache visibility, you know about your volatiles, you synchronize everything perfectly inside an account and you expose the single method called update outside of it. And then you end up in a task, okay, I'm going to make a transfer routine. Well, that should be easy. First, I'm going to invoke update on from, which will properly obtain logs on that object. And then I'm going to, depending on the state of from's balance, I'm going to either wait or I'm going to invoke an update on the to object. This looks nice, looks like a working solution. It probably ends up passing more than just unit tests, but what is very, very, I would say, malicious problem here is that a simple reordering or invoking this method with switched order from to to can cause it to deadlock and to blow up throughout your entire service, which would probably result in lots of unhappy hours in debugging thread dumps and trying to figure out what's the proper order to obtain logs here. It's not only deadlocks and race condition though. You can end up in a significant amount of different scenarios that involves live logs, contention issues, handling interruptions, which is usually completely ignored, even in Java world, and many, many more. What this leads is, again, to the claim from the beginning, concurrency is terrible or your software will explode. But as said, we need to deal with concurrency in our daily jobs. Today, I would like to present an alternative approach to concurrency called software transactional memory. The idea of software transactional memory is not unique to Scala and definitely not a new idea. It has been explored over the years in the literature, and most mature implementation that uses somewhat of a reference for our own implementation exists in Haskell universe and is actually one of the most used and most well-known primitives there. Well, what's the basic idea? What's all the fuss? Well, basically, software transactional memory took the core concepts from the database universe and took that acronym ACID as a guiding principle. From these 4 letters, we immediately discarded durability. We don't need to develop with persisting the data outside of a memory context, but we do need to provide an atomic and isolated approach access to the variables that we are modifying. How does it work? You are building a data structure that we are calling ZSTM, and you are transforming it by applying well-known combinators like flat map and map and zips and everything that we will show up in the rest of the talk. If everything went well, you will invoke commit. Commit here resembles the database commit. So basically whatever we applied so far will either be applied and propagated as the current information, or it will be completely rolled back. For example, if it succeeds, it will commit and it will produce a ZIO effect that is further on executed over ZIO's runtime. However, if some of the variables that participate in transactions were altered and we don't have a grant to commit, our transaction will retry. All of the changes will be aborted or rollbacked, and we will go to the beginning. There is also another possible outcome to this. In some cases, when some of the criteria are matched or during the composition of transactions, you explicitly stated that you want some transaction to fail, during the failure, you will roll back all of the changes to memory representation, and failure will create a failing ZIO effect. What are the characteristics of ZSTM? Well, first of all, it's composable. You get a plethora of combinators that exists in more or less all existing functional effects, and we took ZIO as our API guideline, so to say. It is completely declarative. It doesn't require users to dwell with the super low-level primitives. It doesn't force you to think about the orderings of the locks, to think whether your variables are volatile or not. You just write your Scala code in a functional style, and in the end, you invoke commit. One thing to note is that STM is an optimistic concurrency primitive, so it will at every single point of time, it will try to make progress, and if it's not able, as I said, it will either retry or fails. Note that optimistic concurrency is usually associated with some problems about retry storms, which is a valid point, but there has been work to at least minimize the impact of retry storms in ZIO. But nevertheless, there is still a remark that ZSTM and STMs in general prefer reads than write. And last but not least, it's one of the few, if not the only stack-safe STM implementation in Scala. As of a couple of months ago, we implemented it in a stack-safe manner, such that it works with a transaction of arbitrary length. Usual approach for implementing stack safety in a functional programming world is trampolines. With ZIO STM, we tried different encoding with continuations and I would say controlled or no stack trace exceptions. It worked well, it passed all of our tests, but we still have some room for improvements, which I will talk about later. And last but not least, it's, I would say, moderately performant. Over the past couple of months, we improved performance of common operations and some of the data structures by a magnitude of 20 and even in some cases 100 times. But there is a remark: if you are aiming for super high performance, low latency, STM might not be the right primitive for you. However, if you are just looking for a composable way to scrape up all of the condition variables and lock and have a decent performance, STM is the right choice for you. Note from the past slide that I explicitly mentioned that there is a strict boundary between STM world and ZIO world. This boundary propagates even deeper because you are not allowed to execute arbitrary effects in the STM universe. In STM universe, the only effect that exists is STM itself. Once you invoke commit, you end up in a ZIO universe where you can fiddle up with all of the goodies that ZIO brings, like scheduling, managed, etc. So let's do the hello world of STMs. So the problem is the following. We have two accounts, and for the sake of naming them, let's say one is named Alice and the other one is named Bob. Initially, Alice has $1,000 on her account, while Bob has 0. The problem is that Bob comes and asks Alice to loan him $10,000. Obviously, Alice does not have that amount of money, but there is an additional condition, which is that Alice receives $100 every 10 milliseconds until this transfer completes. So let's start encoding the solution. I will first create a small type alias for account, where I will use a primitive called TREF. TREF is, as we will explore later on, transactional reference, which can participate in ZSTM transactions. To simplify everything, I will say that the count is a TREF of longs. To help me out, build a solution and make the usability a bit better, I will create a small helper in types companion object, where I will set an initial amount. And this will result in a UIO, which is an unexceptional IO from ZIO that contains an account. It's pretty easy to instantiate this one. We will just invoke tref.make commit of the initial value we've been given. Once we have that, we have two more primitives as given by specification. We obviously need some sort of transfer method that will include from account to account, as well as the amount you need to transfer. This will also produce a UIO, and since I don't particularly care about the outcome of this, I can mark the return type as any or as unit, both will suffice. I also have the method which I will call credit, which will take care of updating an account balance as specified above. So this one will be simpler. Let's say something like this. And again, I don't care much about the value produced. So let's try to construct our own program. How would it look? For the sake of brevity, I will extract the program in a separate for comprehension, and I will build Alice's and Bob's account as stated in the specification. So Alice initially has $1,000, and Bob initially has $0. Once I have that, I will do the main, let's say, loop of our program, which will basically say, hey, take a transfer and try to transfer the amount from Alice to Bob, and the amount we need to transfer is 10K. And erase it with crediting the Alice's account. Alice receives $100, and as specification stated, this happens every 10 milliseconds. I've used quite a lot here. I've used a few primitives from ZIO itself. First is race. Race in essence executes two effects in parallel, and once either of them terminates, it will cancel the other one. And I use repeat, but repeat is pretty intuitive DSL, so basically I'm building up a schedule that will allow me to repeat the crediting every 10 milliseconds. And once this terminates, I will just state that I want to collect balances. Balance Alice is just a simple get. I need to commit it as it is transactional. And balance Bob and later on, just for the sake of inspection, I will put the balances on the command line. So let's say Alice has balance ls USD as I noticed there's a question regarding why do I have commit. The commit is here in order to allow me to move from transactional world to ZIO world. Everything here is expressed as a ZIO data type, but if you go to ls.get, it will provide ZSTM of long. In order to go from ZSTM to ZIO, I need to commit the transaction. And last but not least, I'm yielding unit, and I'm formatting everything. So once we have this, we need to implement our transfer and our credit. Let's start with credit because it is easier. In essence, credit will do the following. It will just invoke the update method and simply add an amount. Again, the same remark applies since we are living here in a transactional world. We need to get away from it, and we will invoke commit. For transfer, the stuff gets more interesting. Let's start naively. So we will collect balance from, or let's call it current balance. It is just a simple read from account. We will also do the following. So update minus amount, and we need to do the similar stuff to account. Finally, we will just yield. Now this is getting there, but we are missing one important thing. The important thing is this will cause negative amounts. We are not preventing by any condition or any condition variable, if you want, that you can deduct more than you have. In order to do that, ZSTM comes with a superpower in terms of a combinator called check, which allows you to say that, hey, I'm going to require that this needs to be satisfied in order to proceed. Until this is satisfied, until I have more or equal than the amount on my balance, the transaction won't proceed and it will be returned it will be forced to retry. Finally, to make us go to the ZIO universe, I need to commit the transaction. There are two ways for committing, one being the alias of another. You already saw the commit. However, I personally prefer to use atomically for longer blocks of code because I find that it reads better than just putting a parenthesis over the whole for comprehension and adding .commit in the end. Once we have all of these ingredients set, we can check out whether our setup works. So I'm just switching to terminal and invoking run over example number 3, which will show that eventually, after a few retries, Alice ended up having $700 and Bob ended up having $10,000. The important takeaway from here is that no arbitrary effects participate in STMs, so you can use only various types of transactional references. Transactions can retry based on a specified predicate. And probably the most important for the concerns one, this retry is not causing visible. It's basically suspending a transaction until a change happens in one of the references that it is taking care of. So, for example, here it would be restart once the from is modified. So, let me get back to the slides and let's proceed. We shown some of the building blocks here, but let's explore them a bit more in the following sections. So the first and foremost, basically the building block of ZSTM is so-called transactional reference. Transactional reference inside ZIO is represented by a type called ZTref. As most of the database data types in ZIO, it has a few parameters. Here we encoded errors for input and output type, as well as the input and output type, and it exposes quite a few operations. I've included the most frequently used ones in the slide. So we have an option to read the transactional reference by invoking get. We have an option to unconditionally set it by invoking set, and we have various combinators to set it based on the current state, which are update and modify, as well as their effectful variants. Note that in the example, I've been using an alias called tref. Tref is basically a less powerful variant of ZTref, where everything's been set to nothing and any apart from the output type. Aside from ZTref or using ZTref, we've built up a more powerful notion called ZSTM. Under the hood, ZSTM first of all includes three type parameters, R, E, and A. R is an environment or dependencies needed for transaction to proceed. E is a potential failures, and A is the values that it will produce. As I mentioned here, it is API compatible with ZIO, which means that most of the combinators that you have available for ZIO, you will have available for ZSTM. Obviously, there are some exclusions, and these are mostly stuff that are intended to work with fibers and with schedules, which in ZSTM universe are simply not available, as it's not on the same level of abstraction, so to say. It is important to mention here the relationship between the tref and ZSTM. Under the hood, ZSTM survives due to the existence of journal. And basically, journal is a mutable map that takes care of all of the references that are participating in transaction. And in the end, that journal is simply validated in order to produce a transaction that succeeds or fails. What are the most common operators available on ZIO? Well, on ZSTM, we have, I would say, a couple of groups of them. First group is constructors. Constructors live in ZSTM's companion object as well as the companions of its aliases like STM. And we have a possibility to create transactions from various types available in standard libraries on various literals that you want to provide. So for example, in order to construct an immediately failing transactions, you would invoke fail. If you need to construct STM from either, you have a combinator for that. The same applies for functions, options, tries, as well as capabilities to construct immediate STM that produce an optional value or STM that produce valid either with value either in left or right channel. Once you construct your effect, you will need to transform it somehow. I would say the basic combinator you have at your disposal there is called map, and it's error dual called map error. They are quite intuitive. They operate on error or success or value channel, and they will just transform the transaction value in either way. Here we see two examples of usage. So in first example, we are constructing a succeeding transaction with value of 21. And we are mapping it by duplicating that value. So the outcome in case the transaction succeeds would be 42 or 0 of 42. Similar reasoning applies for the second example, where we are basically just lifting a string failure into an exception with, that uses that string as a message. Besides map, you obviously need to have flat maps and to allow your transactions to change. So we have duals there as well. We have flat map and flat map error that allow us to chain over value or error channels. And this combination grants us the right to execute or transform our transaction through 4 comprehensions as we saw in the example some minutes ago. There are plenty of zips available inside STM. We have the most well-known, which is zip, which basically tuples the values from two transactions. We have zip left, zip right, and zip width. All of the operators comes with emoji dual. So here you can see an example of symbolic operator for zip, which is that app operator Haskellers among us know. Note that for all of these operators, standard rules about transaction retries and failures apply. We have quite a few operators that allow us to recover from failures in one way or another. The most basic one, I would say, is fold and fold M. Fold allows us to recover errors or transform values using pure functions. Fold M allows us the same capability, but with using a factual function. And in this scenario, note that both of these effectful functions provided as f and g in fold M can fail. Therefore, their error type E1 is reflected in the return type of fold M. Fold M is quite powerful, and there are lots of other combinators implemented in terms of it. And below you see one example how you can use fold to recover failed value with either false or true. One of the superpowers ZSTM brings is the ability to check and retry. We saw a small example using check as a condition, and here we are showing that how check is implemented internally. So it basically checks on predicate and it returns unit if that predicate is satisfied. Otherwise, it will force a retry. Besides that, we have a few more combinators. The most useful, I would say, are retry until and retry while, which are somewhat of a DSL cons that allow you to retry until some predicate is satisfied or retry while that predicate is satisfied. They are basically equivalents of filter and filter not on some collections. There is one additional strength of ZSTM and of STMs in general, that's the ability to provide choice or the alternative. So when you are faced with a transaction that fails or retries, you are allowed to provide a fallback to it and saying, hey, okay, maybe you can try the transaction B if transaction A is not succeeding. There are two, I would say, first-class citizens in this group of operators. One is called or else, the other one is called or try. The reason why we have two was somewhat of a dispute, and it has some roots in a history. Basically, in a Haskell universe, when you have two transactions and when both of them are forced to retry, say you have transaction A or else transaction B. If both of them retry, the whole transaction will retry starting from transaction A. But that's not idiomatic for ZIO, and all of the other or else's in ZIO library actually assumes that you would continue your work from the fallback. So if you have transaction A and it fails and you have or else transaction B, it will continue operating on transaction B solely. So all retries on transaction B will stay there. That's why we decided to have an or else, which resembles ZIO behavior, and or try, which resembles Haskell behavior. Both of them have corresponding symbolic operators, and what you see here is a symbolic operator for or else, which basically states in case the first transaction, which is STM fail or failure, fails or retries, continue processing with the second transaction. And once you've transformed and you build up your transaction using flat maps, using zips, and using gaps, or else's, and everything, as we shown on the diagram, you need to go to the ZIO world in order to be able to actually execute your transaction. And that's why you have a commit and its origin called atomically. So either of them are fine. As you can see, commit is implemented in terms of atomically. So you can use both options, either on the companion object or on the the transaction itself, whatever is, I would say, more readable in the concrete use case. Since we are doing a concurrency talk, I believe it's inevitable that we have to do the dining philosophers as an example. So let's see how we can solve dining philosophers problem, which is one of the most well-known concurrency problem in using ZIO STM. So here I have a simple ZIO app that uses a very simple encoding of a fork, seat, and table. So for those who are not aware, dining philosophers is a problem where you're given with n philosophers and n fork. And for a philosopher to eat, he needs to obtain 2 forks that are on his left and on his right side. It's a very interesting concurrency problem because it exercises our safety and exercises our aliveness properties because it prevents starvation of particular fibers or threads, whatever you prefer, and depending on the language you are using. So let's see what we have here. We have a simple implementation of a fork as a case object. And we have a table implemented as chunks of seats, where each seat is basically a case class containing a left and a right fork. These are initially marked as optional because initially you don't have any, you haven't taken any forks for yourself. In table setup, we are basically doing the initialization. This is the code that we don't need to particularly look at. It's basically building a circular representation of a table. And in each method, what we are doing is just invoking take forks. Afterwards, we are invoking put forks. And that's the whole implementation of a dining philosopher's problem in STM world, assuming you have the implementation of take forks and put forks, which are where the core problem lies. If we go to our main, it's doing nothing other than just setting up tables and then forking all philosophers to start beating. Fork all is basically an operator that takes an iterable and starts the computation from that iterable in parallel. Here we are taking philosophers and starting their eating in parallel. So how can this be made to work with ZSTM? We need to implement 2 primitives, take forks and put forks. Let's start with take forks. So each philosopher will take a look on its left and it will take a look on its right as well. The outcome of this will be a tuple, and we need a very specific combination of that tuple. So basically we need this tuple to be available. We need both forks to be available in order to proceed with work. How we can make it? Well, we get the forks. We need to mark them as taken. So we will mark left as taken, and we will mark right as taken as well. And once both of these are marked, we will just return a tuple of obtained fork as required by our method signature. In any other case, we cannot do anything other than retry. Put forks is symmetric to this. You will take a look at your left. You will take a look at your right. You will flat map, and the only thing that differs is that now you are basically requesting this constraint, so both of these are available, and in case both of these are available, let's just say left set forks 1, and then right set forks 2. In all other possible cases, we will go and retry. It has to be wrapped in a sum. And once we have that, we should be good to go. So let's see what we made here. We started philosophers, and as you see from the trace, the first log is produced the moment philosopher expresses the willingness to eat, and basically you see all of the philosophers queuing, and the done eating is printed out once philosopher leaves the fork and finish up eating. Once all 10 of the philosophers created are done, we will end up the simulation. As you can see, it's pretty capable of starting all of them concurrently. And it is also pretty capable of preventing any races among them. And we achieved that in quite a few lines, basically. Just a simple zipping of 2 TREFs and then checking out whether forks are available or not. This implementation with STM is significantly shorter than the usual implementations, I would say, in both Scala and in some imperative languages where you have quite a lot of things to worry about. Here we basically push all of the worrying to the level of STM, and we are just dealing with values over here. So let me continue. Aside from building blocks itself, ZSTM comes with quite a few data structures that you can use. So let's make a round trip and meet each of these. First is tpromise, which is a transactional variant of promise, and it's basically just a wrapper using transactional reference containing option of either of E of A. It exposes all standard operators, so I won't delve into the API, whatever you expect from a promise in ZIO or a promise in standard library you have here. The only difference is the return type, which is of course ZSTM. We have semaphore, which is a generalization of a logs, and it basically contains just a reference of a number of permits available. As of recently, we have reentrant lock, and as far as I know, Kamal did quite an extensive benchmarking here, showing that reentrant lock is performing worse than Java's reentrant lock implementation, but with a significantly fewer lines of code, and the overall performance, I would say, trade-off wasn't all bad. I would provide as a follow-up to the presentation, I can provide the benchmark results, which are quite impressive, I would say. We have transactional queue. It's implemented as a TREF or a simple Scala queue. What's interesting here is that both take and offer are fully back pressured, and the whole implementation, I think, contains no more than 20 lines of code. Of course, you can make a claim that the usual queue implementation, including the one in ZIO, is faster or more performant, and that would be true. But in terms of declaratives, or what John would like to say, superpowers, I think you are aiming for really, really fast wins by using the structures and defining them in this way. Other than this, we have quite a few, I would say, a bit more involving structures. The first of them is array. Array basically contains an array, regular Scala array of references, which in ideal cases gives us a full parallelism. So basically you can access and modify each of the array indices independently. And the T array is used as a building block for TMap, where TMap is being implemented as sort of a classical hash map. So it basically uses chaining, uses an array of buckets, and it uses chaining to resolve the collisions. We have tried to mimic the behavior of hash map in Java in terms of the way how hashes are calculated and how we are allocating when we are doubling the size of the underlying array. And actually, TMap was mostly affected by performance optimization we did recently. In terms of TMap, we have tset, where it's basically just a wrapper over a map that contains unit values, and keys are given as map keys. And recently we've added a implementation of T priority queue, which is implemented in terms of a Scala sorted map and holding reference of it. Note that all of these collections are mutable by their nature. So you don't have composability in terms of that you can map something and then you have a new structure allocated. No, that's not true. We are relying on transaction, on STM fully to provide us consistency of the data that's in our structures. But for the most operations, you will mutate once the data is committed. And I would like to show how you can gain these superpowers by providing an alternative encoding of T priority queue. I think at one point we ended up having this implementation in ZIO itself, but we ended up replacing it for a more general solution. But nevertheless, let's see how easy or how complicated this is to define your own concurrent structure. I have a PQ module and I have a small test program for it. Basically, test program is very elementary. It will create a priority queue and it will shove a bunch of elements into it with higher and lower priority. And my expectation is that when I pull the elements out of a priority queue, I will get them in an ordered fashion. Note that this queue works as a min queue. So let's say min is more, 0 has higher priority than 3. The queues API is very simple. It offers two methods, offer and take, and it is implemented in terms of a TREF and TMap. So we are using two STM primitives to define our third. Map will contain the data stored in the TQ, and it will be map of a priority to a transactional queue. So transactional queue will take care of elements that are actually injected into a priority queue. And other than that, we are adding a min priority. Min priority reference is in essence just a thing that's used for faster lookups because it will allow us to just consult this ref and say, hey, which priority is the next one to be pulled? And once I get it, I will pull the map using that one. So let's start with encoding alpha. In order to add an element to a priority queue, you need to find whether the priority is already stored or not. To determine that, we can invoke a method called get on a TMap, and this method results in an option. So obviously the option will return a queue if the key exists, otherwise you will return none. That being said, we will either need to construct that queue or use the existing one. We can simply determine that by using fold, where in case, or even better, get or else can be done. So basically we are even getting a queue. No, sorry. There is a reason why I need to use fold, and that's lifting in transactional context, sorry. So in order to get this one more time, we will either construct a new queue in case it doesn't exist, or we will just lift it in transactional context. We are lifting the value in order to be able to utilize for comprehensions fully here. Once we have the queue, we will, let me just, we will invoke its offer method using the element A. This offer will provide us fully back pressuring in case that queue is full. Obviously here we created a queue that cannot be overfilled, but in case we limited it in size, offer would work just smoothly to provide us back pressuring for full queues. Once we have stored an element into a queue, we need to do one more thing, which is to tweak the min priority if needed. There are cases where this is obviously needed. So in case the new priority is lower than the current minimum, we will need to do this update. So let's just do it like this. Actually, I don't need this value at all. And I will simply say if current is bigger than given priority, I will set the priority. Otherwise, I would leave it as it is. And that's the offer. Let's see how we can implement take. Take is a bit more involving, as it has to take care of the case what happens when we have drained the queue. When we drain all of the elements of a single queue, we obviously need to change the priority, and it would be good if we remove that queue from our map. So let's start by drafting a for comprehension first, and we will have to first pull out the current minimum priority. We do that by invoking get on that ref we are updating. Once we have it, we will go on and query the underlying map and try to see whether there is more stuff into it. If there is elements in the map, we will take it and prepare it for draining. And if there isn't, if the queue is for some reason empty, we will be forced to retry. And this retry will have something like this. Once we have that, let's just pull out the next element of a queue from a queue. Okay. And it will eventually yield the page. Yeah, and now that we have this, let me see. Yeah. Sorry, my types are obviously wrong. And now we have that, we can proceed. However, before just letting it go, we will need to update min priority and delete elements if needed. So in case the queue is empty, we will do some additional processing. In order to make it a bit more clearer, I would use one of the zips, which is zip left, and I will perform an effect checking out whether queue is empty. And in case the queue is empty, I will just invoke a method called increaseMin on it. Now let me just, this is obviously a fantasy method because it doesn't exist, but let's introduce it. So increaseMin is queried to increase readability. It will take the current minimum and it will take the current queue as well. And it will provide something like this. How it will work. So in case the queue is empty, I will just, oh sorry, I actually don't need it per se. In case the queue is empty, I will do the minimum calculation. So what I need to do is I need to find next minimum. And to obtain new min, I will do the following. So I will basically first delete the current priority, and then I would immediately follow up with invoking keys. Let's just call this priorities. These are remaining priorities in our map. Once we have remaining priorities, let's find the minimum of it. So this can be done by invoking something like min option, get or else, and it's safe to assume that default value, in case there are no more elements, default value should be max values because everything is smaller than it. And once we have it, the last thing we need to do is to set the min priority to no min. And finally, we are yielding back the control. So here, and that should be the proper implementation. I think the only thing I'm lacking is the factory method. So let's construct this queue. As everything, this queue needs to be constructed as well in transactional context. So I'm making an initial min priority and setting it to max value. I am creating an empty map of ints to TQ of A, and I'm just yielding a new priority queue of ref and man. And now we should have it. So let's see whether this works as expected. If we run it, and run example number 1. Maybe not. Maybe not. Let me see. That's fine. And just go back to see quickly whether I make everything. I take each of these. Perhaps. I'm sorry I need to double check because apparently I made a mistake somewhere. Let's see. Yeah, it doesn't print anything, so that's a clear indicator that there is somewhere a race or blocking. If someone sees the issue, it's not me, feel free to point it out. Yeah, obviously. I have modified the queue, but other than modifying, I need to persist the change to the map. Otherwise, it won't work. Now it should be fine. Yeah. So now, as you can see, it stored all of the elements. It pulled first all of the 10 elements with zeros, then it's continuing to pull out all of the elements with priority of 3, and then it's waiting for me to terminate the whole program. That's the Perks of doing a live demo. Sorry for that. So, once we've done with priority queue encoding, I just want to give a glimpse into the future. So as I mentioned, we have a stack safe implementation, but our current implementation is done in terms of continuations and exceptions that do not generate stack traces, but rather are thrown for the flow control. I've done some benchmark in the background of this, and I found out that actual trunk line encoding, as the one we are using in ZIO, is slightly more performance in certain cases. So the current work in progress is to convert the stack safety mechanism that powers up the ZIO. We have quite a lot of performance improvements or possibilities other than that by using some unsafe combinators. And the biggest goal, I would say, but the goal that's definitely post 1.0 work, is to come up with the saga pattern in STM. While I mentioned that that ZIO effects are no-go in ZSTM world, there might be a way to make them friendly to the STM world and to provide a certain classes of IO effects that could be run in a transactional context, which would allow us to provide immediately the effect and the fallback that should be done in order to roll back the applied action. This would allow us to encode the saga pattern in terms of ZSTM, but this is a highly experimental work, and in case you are interested in participating, please reach out to me. And if you want to learn more about this, you should check out the two foundational papers, which is composable memory transactions and log-free data structures, as well as the implementations of STM present in ZIO and Haskell at the moment. Last but not least, join us on Discord, check out the ZIO repo. There are plenty of good first issues to work and plenty of advanced issues that you can find someone to pair with or someone to mentor. Last but not least, thanks to all of you for attending. Thanks, John and Courtney, for having me here. And now I'll be taking up your questions.
Thank you. That was wonderful and lots of information for us all to, ingest, think about. So questions. So the first one that we have is, if the method offer, and in parentheses, when does the queue get added to the map?
Yeah, that's the issue that I struggled with. So let me open up the code. In method offer, queue gets added to the map after the offer. So obviously I'm invoking offer, and once the element has been offered, I am invoking put to put the updated queue back to map. So by updated queue, that could be a queue that just been added with its first element, or that could be queue that has been expanded. That was the issue that caused the program not to run, because I omitted this line. Basically, I omitted the part where I'm persisting back the changes.
Okay. So thank you. So somebody was saying, somehow I thought that the program for comprehension or flat map calls were mixing up STM and ZIO. Can you speak to that?
Yes, that was, I think, in the first example. We have most cases there. Basically, the program which we have here in for comprehension is purely ZIO values. So if you check out the type, you will see that the outcome is just a ZIO that requires block and console and produces unit. But we are using some methods that are transactional under the hood. So for example, these gets on TREFs, they both produce an STM. And as I said, to make these two work together, we need to go from one universe to the another. So in order to go from the universe of transactions, which is alice.get, to the universe of ZIO, we need to invoke commit explicitly. And that's what I'm doing here. So for all the transactional methods, I'm just adding .commit. I am operating here on the level of ZIO because all of the operators I'm having, like raise and repeat, these are ZIO operators. They are not present in the level of STM. But there are also examples of using for comprehensions with purely STM values, as we can see in transfer function. Everything here is just an STM data type, which I'm committing as the output.
Next question. From what I understand, this is valid to a single machine, but not to a cluster. Is that correct?
That's absolutely correct. So STM covers this, the case of single node memory transactions. There should be a project somewhere around in ZIO ecosystem that's called ZIO distributed, and plan for that project is to cover distributed transactions. But for more information, I think persons you need to ask about it are John and Francis Dodd.
There you go. Ask John. Next question. Should we wrap take in STM dot atomically?
I'm not sure at which exact state I presume you're thinking about this one, but note that this is already wrapped. This is not a Scala queue we are operating, but rather a transactional queue. So the part that you are telling about is already taken care of by the API. If you go to the take method, it's doing exactly that. So it's basically producing a transaction that will do the dequeuing from the underlying Scala queue.
All right, next question. I see you put a TQ in a TMap to be safe. I think it's a general rule. Any STM data structure, if held safely inside another Scala data structure, then that data structure cannot be Scala STDLIB stable, but ZIO STM is one.
Yeah, this goes in general way how we are defining. So in general, in functional universe, we basically never produce something that's uncontrolled. So if you are in STM context, you would create your structure in an STM context. So when you build up a ref, the result of your operation would be a STM containing a ref as an output. And same is done here. So you have something that wraps a concrete structure.
Okay, so there was a retry while constructs were mentioned. Is there some way to time out or influence interval between the retries if conditions are not met?
There is no way to time out because there's nothing to time out. So this is not a busy loop. Retry is not spinning around and waiting for things to change. Retry is actually suspended completely until some of the address reference changes. Once the address reference changes, the whole operation is started from the beginning. So there's no timeout needed to really encode or postpone anything. Note, however, there is a caveat. Obviously, shorter transactions are preferred than longer ones, and obviously reads are preferred than compared to writes because they just read, they don't modify anything. In order to mitigate potential retry storms, we did a trick. A trick in essence consists, if we find out a single transaction retrying more than a certain amount of times, which is currently completely heuristic based amount, we will at that point say, okay, you've been restarting for some time, you've been restarting say 10 or 20 times. Now here you go, there's a global lock, obtain it, do your work, finish it up and return me the lock. So we will basically at that particular point, we will prioritize the transaction that's been retrying for a while.
Okay, so somebody who had asked previous, I think it was that question, said that you indirectly answered his question by using STM to update the map after changing the queue inside that map. So that map critically is STM.
Yeah.
I think that was more of a comment. And then I think the last thing that we have so far is somebody was interested in looking at the second to the last slide.
Yes, we can go. I will open the second to the last slide. Here it is, and I will paste up a Discord link in a LambdaConf channel as well. So
yeah, okay, there we go.
Directly
I think
access
that's
it.
what it was looking for. All right.
Yeah.
So that's all the questions we have, unless somebody else chimes in. So thank you so much for this, and for adding the STM to ZIO.
Yeah, off topic to Paul, it's I3.
Yes. So a big thank you to you and to to you for all this. Thank you very much.
Thank you for organizing it.